Is it what I call protomatter, just protons, electrons, if you will?
Yeah, you can actually almost work out how this stuff should be segregated into layers by, like the mainstream model. When they wrote that paper, they started with an idea of, protons, electrons, and the only other thing was to combine those into like hydrogen.
Welcome to the April 23rd edition of the Electric View. I'm Neil Thompson. Today we have David, Buddy, Edwin, Heather, Jim, and Robert. We tackle the topic of what a star is, how they really work, and what evidence we have for any particular stellar model. Don't forget to like and subscribe down below.
Let me ask you the question a little bit different then. In the interior of a star, right? Mm-hmm. Deep down, way beneath the layer that you pointed out, can atoms exist there, stable, or will they disintegrate, in your view?
Well, what should happen is you get the whole thing happening all over again. And inside that, there should be a limit to how much you can have the whole thing happening all over again inside at a smaller scale. I mean, that's how they got I think that's how Edmund Halley argued for the concentric shells idea. But that should happen inside the solar surface too. Like, again, if you look at what happens on the heliospheric scale, I mean, there you have a nice charged double, a fairly spherical double layer too. And inside, that doesn't stop there from being things like, the sun and planets obviously orbit inside that, but that spherical double layer is again kind of the same thing, where they see a density higher outside of that than inside too, and that's.
I'm trying to get to what is the star actually made up of? What is its composition, physically and chemically, if you will, and electrically?
That's quite hard.
Say again, Neil.
Hello. It's just quite hard to tell, I mean, because we normally detect it, like you can use spectroscopy to determine what's on the outside of a star. You can do that. But ooh, that looks cool.
The shrimp guy?
Yeah, that's the two solar winds in the heliosphere. So those are the currents that are connecting it. That's nice. You get to see those. Because the heliopause is in the middle. But anyway, besides looking at that cool thing on the screen, what I meant was that this is the reason where you get the division between someone like Robitaille and someone like Wall Thornhill. Wall is arguing that gravity changes and or mass changes, one of the two, and Robitaille is not allowed to say that, so to speak. So he went with a liquid hydrogen model.
Metallic hydrogen, indeed.
Exactly, because he has to deal with that density problem. Whereas, when you look at comets and you say, hey, that's a rock, and then, oh, but it weighs as much as a dirty snowball. Well, why does it look like it weighs like snow? It looks like rock. And then, of course, Wall is like, because the density is different, stupid. It's not, the mass is different, that type of thing. So determining what's inside a planet now, what's inside of the Earth doesn't have to have a metallic core. Those things don't have to be gas giants. The sun doesn't have to be hydrogen. All of that is all thrown out if we go with Wall's idea.
But you mentioned spectroscopy, right? Now, there are a lot of those, a lot of that equipment in spectroscopy is looking at the sun. Can somebody tell me how far they can look down and tell me what chemistry or what lines they see? What do they see? Do they see hydrogen? Do they see, helium? Do they see nothing? Do they see only X-rays?
Oh, no.
What's up?
I think that they can see right down to the iron surface, or an iron. There's an iron layer to it.
An iron layer.
Yes. Yeah, if you look up, in fact, you could probably type it in, the sun in iron, like the iron layer of the sun or something. I remember that was one of my favorite, because it was green or something, and I'm not sure why I'm not seeing it here, but you can see the surface, and you can see like mountain ranges and stuff. It's very compelling.
Why is it iron?
I have no idea. Here, Jim, you guys were having a great conversation when I interrupted. I just saw that. I'll go and try to find that.
I'm trying to get at something fundamental here. When we look at stars, like the sun, now, what is it made of? I'm sorry. Can anybody help me out here? Because if we cannot even answer the question, well, at least those elements are there, and there's probably something such and such a mass, and it looks like hard rock, or maybe water, or maybe gas, or maybe a plasma. Help me out. Can we reach consensus there?
No.
No.
What information?
Perhaps we can see.
What information do we have? Jim, you're very knowledgeable in this arena. Can you help us out here?
Yeah, we'll see.
There we go.
The problems where everything is. What should happen? I mean, even from the EU model, is that we should have these shells, but they should be really finely compacted. The difference you would expect to see is because of the basically the balance of gravitational and electrostatic forces. It should sort that material into shells, but these shouldn't be like radically different percentage differences into or out of the sun, and that's where it gets kind of hard to trust the mainstream observations are kind of hard to interpret in a lot of ways, because so much is seeing what they want to see, and how you know that they're not right is that a lot of the effects that we should be seeing if we're in an electric universe, that you would wonder why they don't know, with things like the Stark effect and Zeeman effect. Why don't they already know that that there's electric and magnetic fields on the scale that EU is talking about? So right there, you know that they're not seeing things quite the right way. But then you also have it's basically buggered up because of things like Don Scott's model, how the magnetic field rotates. That masks the Faraday rotation measurements of magnetic fields. So what's going to happen is there's so much that really is going on, like with line splitting because of the Zeeman effect, line splitting because of the Stark effect. One is magnetic fields, one's electric fields, and then there's shifting of spectrum from actually Doppler shifts, like if there's thermal currents going up and down and all that kind of stuff. But what it really means, though, when you're looking at the spectroscopic
I'll keep that
material,
in for him. Yep.
Well, the most important thing to realize is the mainstream. It's a complicated mess. What the mainstream has going for them is that they already know what they should be seeing according to their theories, and then they do match their observations to that. I mean,
exactly. And we're
almost by
force.
Force. I'm sorry. That's the problem I have with it. It's like when they made predictions about the cosmic microwave background, and their arguments was it should be around 50 degrees Kelvin, and then the people who worked on the steady state said it should be 3, and or plasma should be 3 or 2.8 according to Peratt. And then it turns out that they just adjusted all their models to say that they were right all along. Like, that's the problem. They just obfuscate their hidden thing. But just like we're seeing here, there is, with those two effects, the Zeeman effect and the Stark effect, you get a widening of the lines in one, and of course the other one is they get moved up or down. I'm not sure, but I think that's the two of them.
Right, yeah, there's splitting of lines, there's widening of lines, there's even the Doppler effect. See, it's more complicated than they make it seem, because it's not like the surface of the sun is entirely coming towards you or away from you. There's a whole range of atoms moving, or, ions moving.
I understand that, but if we were to look at the bulk in the center, what would you say is it made of? Is it made up of hydrogen atoms? Or is it strictly protons and some electrons? Or is it actual all kinds of elements?
Well,
there should in fact be all kinds of elements torn apart differently at different depths.
Torn apart.
Again, by that's where you get with that balance of
right, because
gravity and electrostatics. To me, that's the main.
Because when we look at this picture here, I'm going to try and make a connection. Can you blow that one up a little bit, David? Yeah.
Yeah, good.
This is, I have no clue where the picture belongs to, but it strikes me as being just about the spectrum that we read in the solar wind. Because hydrogen is, of course, most abundant, that we know. Helium is quite abundant, right? It gets transported a little bit. But then comes suddenly oxygen, I believe, as the third one. And then you get carbon and magnesium. And some nitrogen and some, maybe a sulfur here and there, a little bit neon, but that's about it. But the first ones, the ones that you see here, those elements are the ones that are prevalent or dominant in the solar wind. So that tells me something about the function of a star. It tells me if there is a constant thing, and those elements are really most abundant, and they are, you're talking about, out of 1,080,000 oxygen atoms. Out of 1 million. That's quite abundant. Something to that effect. So that tells me what the star is doing. The star, in my book, is producing those elements. And it must be producing that in the end from hydrogen. Right? A fusion process. So, of course, the questions we have, where is the fusion happening? But I think through the talk that we're having now is, okay, let's start figuring out what a star actually does. Because what Jim is alluding to is that at deeper down, it's more like a destruction factory than a creation factory. Am I right?
Well, yeah, if you're talking about like neutral matter coming in from the outside, then yeah, it should tear it apart into its
and rearrange it into its materials that it's going. Yeah, that's what I see.
Just
yes.
That key point is that however you want to explain it, it doesn't matter. But protons are 2,000 times as massive as electrons, and that dynamic is where that's what the mainstream totally missed when they got this idea that neutral matter would form neutron stars. Well, yes,
about those neutrons and neutron stars, you guys may know about that, but I don't think there is such a thing as a neutron particle, right? It's always a connection between an electron and a proton.
Exactly, but that even more so then that if a neutron is that, then when you bring a neutron into a strong enough gravitational field, it also has to tear it apart into its constituent components. So what it means is that in a strong enough gravitational field, you can't even have a neutron.
And therefore you cannot element.
Yeah.
Well, and that's actually very much what Donald Scott had argued anyway. He said there's no way you can make an atom, basically what you're saying is make an atom of neutrons that's 12 miles across. You can't do that. It's just, it violates the axial stability and everything. But
the pressure and the density stacking would totally prevent any element to exist stable for a long time. Even if it wants to be stable on its own, the environment will be so pressing, it will distort. Right?
Well, and of course, voltage pressure alone would rip things apart, as we've seen. I mean, According to our
Yes.
understanding, we only have 500,000 volts on Earth, and there's probably like billions of volts on the sun. The potential difference between the atmosphere around the sun and the sun, like the
Right.
surface of it. We can't obviously measure that because nothing can get down that low to measure the voltage. But I mean, we have tornadoes, and they have, 300-mile tall pillars of fire making up the surface of the sun.
And it's not
anodes.
exactly one.
Yeah, so there's
It's the whole surface, right?
exactly. And of course only with sunspots do we see below that. I made a
Yes.
link, by the way, there, Dave,
Mm.
that showed
Yeah.
two little things about the surface of the sun. One's that website, and the other one is a question that references that website. But I thought it was interesting because the bottom one says, well, 100 years ago, they thought the sun was iron. And they did, and there, someone was talking about it. You are not misinformed, see? And an interesting history behind the idea that the sun is made of iron is a fairly recent question. And where is the source of energy? Just at the last paragraph there. And they're talking about what caused it. And 150 years ago, it was realized radiation was used to measure its temperature, giving a surface temperature, yada, 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 yada. But we thought the sun was, the 200 years ago, the question wasn't even thought of, but 150 years ago, they thought the sun might be made of iron because of this spectroscopy. But the website above that, which is the surface of the sun, shows you pictures of that surface. So it's very, very interesting. You can see places that don't move on the iron layer. There's things like we should see mountain ranges, quote unquote, moving along if the sun is electric. It should be, but it looks like these prominences and stuff, just where these loops are that Andy was talking about on Earth, are connected to like mountain ranges, and they come off the top of them and they go into plains and everything else. So we see, and they don't seem to move. They seem to go with the surface, like the main surface, the actual slowly rotating one underneath, because the atmosphere spins faster than it's differential by latitude and depth, as Don Scott has pointed out. So, Terrellas. Very nice. Anyway, I just thought that you might be interested in the surface. Yeah, see little planets doing planet things. There's our glowing blue aura around Saturn that we see. I don't know if you noticed it. It does have a little blue aura on it. This is how auroras get made. How Io and other planets are etched. I mean, with experiments like this that you can find in a friggin' lab on YouTube, and they can't figure this out in space, boggles me a little bit, It's like, well, we see these tufts coming off the top of Io or the top of Enceladus, and it seems to be pulling material off and making a ring circuit, or going and adding to the ring around Jupiter. And, well, look at this thing. I mean, yeah, that's what it does, dummy. I want to say that. But anyway, so yeah, that's why they were arguing the surface of the sun. There is a surface, and of course, this became only ridiculous 100 years ago with Eddington when in 1926, he put out that book, The Internal Constitution of Stars, and said, well, look, the mass of the sun is hydrogen. Therefore, and the mass of that, the density of that planet is gas, because of its weight and everything, and that's what it is. And we went along with that and never argued,
And that's probably where everything went awry. So if we look at stars, we cannot say, and we take the sun and say, that's what all stars look alike, right? There are super red giants, super blue giants, there are white dwarfs, there are stars like ours, there are, all kinds of other stuff, allegedly, like black holes and whatnot. But
allegedly.
But there is something like big explosions going on, something they call supernova, whatever that may be. Neil, I think you can talk to that one even more. Oh. But what I'm trying to point out is there's a life cycle to stars. So there are really young stars, very hydrogen-like, if you will, right? Very low in heavier elements. Stars tend to produce carbon and oxygen predominantly. The older they get, the more oxygen and carbon they get. Well, helium too, of course. First we get helium, and from the helium we get a carbon, 3 heliums becomes carbon. And a carbon plus a helium becomes an oxygen. That's why oxygen is already so abundant. That stuff gets blown out into space. So by looking at the chemical composition, we can say something about what kind of fusion processes are going on and how far in its development it is. This is all mainstream, but it seems to be more or less holding up, right?
No.
White dwarfs are, and this is because of the iron, Neil. I definitely do not throw away the notion that the sun could be an iron thing or whatever.
Oh, that's his call. I don't know. So.
Well, there's something to it because white dwarfs are more or less Earth-sized objects that have predominantly carbon and oxygen and or heavier elements such as silicon and iron and calcium, etc. But they start out with the carbon and oxygen. The lighter elements are more or less gone, right? And they start fusing into heavier elements. And they are allegedly 25,000 Kelvin or so. Now, you mentioned the other time, Neil, that when you would take away the sun, in response to my question, what would happen to Jupiter? You said something to the effect of it would become the sun.
It would glow white. It would
start glowing, more active, more sun-like at least,
probably,
right?
Well, okay. If you go to the electricosmos.org website and go look at the helioseismology thing that Don Scott had, he has the HR diagram put into electric. That's it, yeah. .org, and then go down to web pages that go up a little bit. Web pages that summarize the book content. Click on that, and then should go down, and there should be electric sky, and one should be our sun or stars. Stars. Go with stars. Actually, back to stars. That's the one. Okay, so there's the HR diagram, but put into.
Exactly what I'm alluding to.
Right, and notice at the bottom, instead of he has age or something to it, at the other one he basically puts amps per square meter. So the surface of all the bodies in the solar system must process all the electrons flowing through it. Rules of electricity say that if it's on a chain, which is a series circuit, then all of them must have the same electrons processed. So they all must be taking the same current. So the only difference then is the amount of surface area you have to play with. Now, if the sun, which is the majority of surface area of the entire solar system, disappeared, and it's already glowing yellow, then adding all that surface area up, and then only what we have left is all the planets. They would have to process all of those amps. And therefore, clearly, the gas giants would be white dwarfs. They would be friggin' hot. They would be like really, a lot of electrons would be going through them. We would probably be completely glowing as well. And, our planet would be probably in the process of killing all life on it. So it would probably be pretty nasty. But you can imagine then that it's really amount to how much surface do you have to play with and how much current you have to process. And that's really the difference. When you get to red giants, it's a bit weird because what happens is, notice it doesn't go below a certain point, but that a red giant, for example, Betelgeuse, apparently is shrinking at about 540 miles an hour. And they don't know why. But according to Don Scott and others, the reason it's doing that is because it's actually it's only in glow mode. That's all it is. It's in glow mode, and we're seeing the outer tuft, the red outer tuft of it. So it's basically, imagine the entire heliopause of the sun. But as we turn down the current, and we keep lowering and lowering, eventually it goes from arc mode, which keeps everything right near the surface of the sun, to glow mode. And so it would just begin to fan out, you'd be able to see the solar wind. And we'd end up having a large red bubble around the sun. And that red bubble would fill the entire heliopause out past Pluto. So that is why we see red giants. And that's why
Keep in mind there is this life cycle going on, meaning the lighter elements have more or less been burned up for a phase like a red giant.
Actually, in this model, there's no need. I don't know for sure. And Jim, you can go next. I don't know for sure. I just want to accurately.
I think there's a correlation. That's what I'm trying to say. But.
And there could be. In fact, I'm leaving it to your brains to help me figure that out. Actually, but there's clearly some. But there's basically, from what from what it seems to be, that it's just a matter of turning it up and turning down the amperage. What can be turned into fusion? It just has to do with if we keep cranking her up, we're going to have more electrical pressure. If we have more electrical pressure and electrical voltage, we're going to have different elements. So
different elements, different expressions at least, right?
That's my feeling.
Now imagine this white dwarf, which was a star like the sun, having more and more carbon and oxygen, turning that, as I tried to point out, probably into silicon and then calcium and then iron, right, by adding oxygen again. There are stars that have very low oxygen. Surprise, surprise, it's being used up. If that thing, which is so hot, which the Earth would be as well if it were on its own in space, as you point out so eloquently,
probably a white dwarf,
Earth would already be almost like a white dwarf.
Yes.
Except that the fusion processes will be much lower because we already have so much heavier elements. The heavier an element becomes, the more endothermic the reaction becomes. Above iron, it's endothermic, so it stops, and then it cools down. But even if I had a white dwarf halfway, semi-active, and if I were to pluck it out of space and put it in the orbit of Earth, replace it with Earth, replace Earth with the white dwarf, would it not suddenly totally cool down and become a Venus-like object, maybe?
Well, this is the argument that I was making before, which was basically we don't know what stars are, therefore they might all be the same things. Like they might be like planets and moons. But here's the thing that just hit me, actually, is why iron. I was thinking, and you mentioned endothermic reaction. That's the second thing that iron does that's very weird. Iron also, quote unquote, conducts like a mofo, and also it will concentrate magnetic fields. It totally draws in magnetic fields in the area and concentrates. That's why we use soft iron as the core of transformers to make the whole process more efficient. So, in my understanding of this, then, a sun or stars being made of iron makes a lot of sense. You're pulling in the magnetic field.
They become it.
Well, they're pulling the Birkeland current right into it, and it would just and it would concentrate it, therefore increase its potential voltage, therefore make more reactions. Seems to be what we're seeing. So, because you have to be able to reach to iron, and then you can go further if you have more current going through it. So
then it uses it up again, but now it's so endothermic that it kills the current, if you will.
Well, it'll keep the concentration, but it's going to keep on mangling. I don't see an age issue here. I only see what it has for quote-unquote fuel. It's going to the surface, once it's hardened into an iron shell, I don't see it's going to have volcanism or whatever's going on underneath, of course. The sun having volcanoes is just a weird idea now, but let's imagine it. So there's going to be currents going through this just like there are on the Earth. But we have no ability. That's the only way that stuff is going to get from inside that shell of iron out beyond that. In fact, iron is very conductive. It lets electricity go right through it. So if this is the case, there might be a situation where a lot of stars are iron. It could be the natural
maybe that's the cause for the magnetic field. Just an iron core there.
Well, the whole thing being iron. What seems to be, like we talked about this again, and this is one of the debates, is the sun hollow? Is the hollowness of an object what makes its magnetic field by having an internal current spin? But God, this is all speculative now. We're on uncharted territory, so to speak. trying to
Well,
figure
okay, let's go to Jim, because he was
Yeah.
trying to say something too.
And we
Jim, what do you
rudely
think of the
interrupted.
notion of that stars actually can evolve into planets? And the iron core, and magnetic field? Can you allude to this?
Well, first idea of, and yeah, it's not definitely an evolution. I mean, we see stars. It came up even in those the records that supposedly Sirius, which is a hot blue star now, was supposedly a red star like 500 BC or something like that.
Yes, I heard that.
But there's other other arguments that it goes that way too, and that's not supposed to happen in the mainstream model. A hot blue star cools off into a burned out old red star. But clearly, if you believe that story happened with Sirius, and you can see if you look at pictures of the local interstellar cloud, you might have a hint of why that happened. I mean, you can see by its motion compared to these clouds, and that's an observation we're stuck with too, is that there is a pattern there. Like this, if you look at red stars around us, like Arcturus and Barnard's star, what should strike you about both of them is that they both have extremely high proper motions compared to the sun, but specifically they're in the opposite direction compared to, from our reference frame, it's the opposite to where the direction we're moving. So what I'm trying to get, instead of looking at how they're moving relative to us, if you look at how they're moving relative to the background clouds, they're really just slower moving stars. So that gives you a whole different picture of what's really going on with stars, and why they might change in color like Sirius did if it's
I love you, Jim.
changing to Well,
You blew my mind. That was great. You blew my mind on that, because I was just wondering to myself, oh, I never even friggin' thought that the actual, because that's what comets do. Comets end up getting closer to the sun and therefore begin to discharge because they are traveling. And I was like, oh yeah, well our star is, has a motion, and I keep understanding this relative motion. Is it being pulled along? It's not gravity that holds it to this galaxy. There's obviously something else. And these, and of course, is it traveling away from, going with the flow of electricity, so to speak, or is it going against the grain? Those type of things.
Yeah, like with the star Arcturus, what you have to realize that its proper motion across the sky is pretty much down through the ecliptic plane. The idea that you get from guys like Don Scott is that we're moving towards the north ecliptic pole. I mean, this is the thing that Michael Claridge too tried to illustrate, and I did too. And this idea that the solar system is propagating towards the north polar direction. Then what should happen if there are any local stars moving seemingly in the opposite direction? When we think we're moving around 220 kilometers per second in one way, if something seems to be moving 122 kilometers per second in the opposite direction, it really means it's moving slower in the same direction we are. And that's.
But regardless of the moving, it's moving in relation. A comet moves in relation to the sun, meaning it comes in a differently charged environment. Therefore, it becomes active. So, what I think is really important here: what is the environment of a star? How active is a star? That in its environment, its number of electrons, the gas, the plasma in space, how dense it is, that will be important. The current that's flowing through it, that will be important. So maybe not so much the speed, but its environment. Of course, in relation with speed, there's a strong relationship there, right? But I think that will be very important.
That's why I like, in the mainstream, there's a Professor Priscilla, I'm going to mispronounce it because I'm used to doing all my reading rather than speaking. But yeah, she was the expert on that local cloud and a sun's motion towards it. And she has so much, she was kind of like a head of a research team, and she knows all these details about it from the mainstream perspective. And there's so many weird things that are happening that don't make sense even to them. For example, that in the last 40 years or something, those blue arrows that they show in that picture, they've changed their direction by something like 4 to 7 degrees. Now, that doesn't sound like a lot, but in 40 years' time, that's a huge difference in interstellar wind direction that you have to explain. But she's also interested in that as you can see, the cloud density. I'm going to use all mainstream terminology.
Of course.
The cloud density is quite different in regions ahead of us, and she's interested in, even from the mainstream perspective, what will happen when our heliosphere hits and ionizes that we should see, even in the mainstream view, we should see an influx of charged particles just because the heliosphere should ionize all that neutral gas and dust that those clouds are supposedly in the mainstream. Our heliosphere should ionize that stuff, and we should see charged particles, perhaps bombarding us.
Well, because if the power's external, it's not nuclear fusion that's ionizing shit. Sorry for swearing. It's not ionizing anything. It's the actual process of the electrons, and we're passing through. Instead of we should say these clouds represent different layers of ionization, different current densities, not just mass densities, but there's probably different currents running through them, and we don't know. I mean, I have an idea that we're attached to the outside of one of these currents. It seems one of these shells of current.
We're in the mainstream articles, we're skimming along the surface of the local interstellar cloud, and they know the magnetic field is parallel to the surface. They know we're streaming along that surface. They know that there's electrons pinned to that surface. So back when I first got into EU, that single topic, the local interstellar cloud, that was where I just dove into all the mainstream research on that, because I knew the answers were going to be in there for what's happening, like how stars are moving relative to that. What are the magnetic fields of that? What other stars are strung with us on that? And that's where you see Sirius behind us and moving. And in the local interstellar cloud picture, you can see why Sirius did what it did. If you look at that image to the local interstellar, that one right there, and you see where Sirius fits in that. Keep in mind that Sirius is traveling more or less behind the sun. It's the sun is supposed to be moving 220 kilometers per hour around the galaxy. Sirius has if you can trust the radial velocities, is moving 8.6. It's slowly catching up. I wouldn't even trust that velocity, but the whole point is Sirius is moving more or less into that region. Sirius supposedly was a red star. You can see where it is right now. And in 500 AD, somehow it turned to a blue star. You can see that if it really came into this region where it is, that explains where it should be getting this current. You can almost see it in the picture. And this is where I was going to if you look at Wallace-Thornhill's model for how something came in on an oblique angle to where our solar system was in the past, I would put it back. Look what happened back in our history when we were by Sirius. What is going on right there? Is that another filamentary cloud crossing ours in the past? That's when you're looking at too for that event. This is a map of where we were and knowing that, you remember what Wall would say, that our solar system, we had a red star for the main star, whatever reason that was. Well, if you believe that Sirius was red and then turned to blue, then it is possible it sun was back there, without even positing a mechanism, if our sun was back there, our sun could have been a red star too, and now, supposedly, now yellow hot, or not serious hot, but there's clues in that picture. That's where I was fascinated for.
Well, we don't. Yeah, we don't know if we're going to go up or down, but clearly, if it changes density of the material it's going through, well, I mean, not even density of material, but whatever current it's passing through. I don't know if that dark area is carrying more current. It could be more electrons versus more ions. I don't really know. But as you said, there's electrons sticking to one of the surfaces. It's going to try to steal that information if it can, or steal the current if it can. And Sirius could be going from a dark area to one with more current density, and therefore it's turning blue. Or, well, that would be my interpretation. It's getting more electrons to process. That's what I'm seeing here. And so, yeah, this whole thing could change. Very interesting. Let's put these little...
What are these things?
Well, this seems to be indicating comets.
If the color changes...
Stars with planets.
If that color change is real, right, from a red giant to a blue giant or vice versa, then the whole evolution model would fall through.
It does. That's my opinion. Yeah.
Right.
And
now, that doesn't mean, though, that there's the correlation that Ito's talking about with different elements and different colors of stars. That doesn't mean that's wrong. It just means that we have to be able to go.
Well, that's basically the mainstream version that I connected there. But what I'm personally think is more important to point out, the way I see stars is as the breeding chamber of the lighter elements, and either the star itself or the shedding of all those lighter elements accumulating of other objects. That's the cause that we can even have planetary objects with life on it, for example, right? Either way, I'm not biased. I'm not looking for my version. I'm trying to find the truth here, like all you guys, right?
I agree.
But if the color changes, and the color is representative amongst other things for the elements that are there, and of course it's correlated to what kind of fusion processes are happening, because they are happening. I think we all agree that they are happening there, wherever it exactly is on a star, right? Mm-hmm. But if that color change is real, and we can point that out for real with evidence, then we can show that it's correlated to the outside material, not the inner center nuclear fusion, right? Then it's an outside thing. If the fusion processes / color changes due to its environment, that would be a strong correlation.
Interestingly enough, if we can nail down some of these numbers, you would know what you need for current density to produce certain elements. Like if this correlation holds true, and we're like, okay, these hotter stars, we'll use the term with air quotes, but these stars with higher current density that are glowing different colors produce different elements, as we have seen via the spectroscopy. If this is the case, then if we could figure out the current density of the sun and so forth, and figure out the equivalent current density of a blue giant or a blue star or whatever, putting this two and two together, we could look down on Earth and go, well, if we have this much current, we can make these elements.
At least we can make a correlation of the color, the current, and of course the other factor which you have to play with, Neil, is what elements do I feed it, right? Do I only feed it hydrogen? Do I feed it carbon and helium? Right? Different outcome, different process.
Well, okay, so fair enough. I never really thought about that. I was sort of picturing just
that would be
shaking a bucket of hydrogen, with a little bit of hydrogen ions and a little bit of whatever, and just shaking that bucket and pouring it onto the sun. Like it's good.
Yeah, but it can be carbohydrates and carbohydrates as well. There are whole clouds in space of kind of molecular stuff, almost biological stuff, amino acids and stuff. There are whole clouds of them. There are stars that made up.
sorry. Please go on. You were saying something cool, and I was interrupting. I thought you were done.
Well, the other variable would be, of course, what are you feeding it with? So you have at least those two variables and maybe a couple of other minor variables, but those two would be the main variables then. And then you can make the correlation slowly by figuring all that stuff out. Indeed, when do we get what kind of fusion and what density is required? Yes, that could be.
I picture 50 years from now. Now that I've been listening to this,
it'll take some time.
Well, no. I just picture me, you, and Jim, and others just standing around a box and going, "All right, well, we need to make some gold, so let's just crank the voltage up to here, and then we pour in some nitrogen, a little bit of poof, and then
who knows?
Coming out at the end, But that would be wonderful if we were at that level of control. But it shows us that nature's surprises are still there, and the fact that we're having this conversation, and it makes so much logical sense that what we're seeing really just alone throws the mainstream into a whack, because they don't even have a clue how they would get some of these elements, and we're like, oh yeah, this is how you make them, this is how you do it, we need a voltage differential here to here, and here's the surface current, there you go. What's so hard, guys? Come on.
Well, mainstream model is quite simple. First, it burns hydrogen, it becomes helium, and then the hydrogen is gone, and you have only helium left, or at least in the center. And then the helium becomes carbon, and the carbon plus the helium becomes an oxygen. But hang on, 2 carbons becomes magnesium. Right, now we have a magnesium layer, and then we double that, then we have, I don't know how they go. They double certain things. They have a neon layer, they have a silicon layer, they have an argon layer, or whatever. But even they have a noble gas layer, and the other one is a metal-like layer. Can you imagine that in a star?
Nope.
No, me neither. But this is the model to come to the heavier elements in stars until they reach iron, and then you get the supernova, and that creates all the uranium that's found distributed on the Earth, right? That's the mainstream model.
I think their argument comes from a very simple understanding that random collisions, which is heat, can produce these effects, possibly. If we calculate the energy and yada, 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 and this is, blah, 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 nuclear reaction, Fermi and all that stuff. But with an electrical interpretation, basically with current density, imagine this if you would. Instead of putting a bunch of material together of the proper constituents that you had previously mentioned in this nuclear thing, 2 magnesiums make an iron or whatever, these 2 elements have to randomly collide via heat. That's why you need millions and millions of degrees to make this type of thing happen. However, if you force them to go in opposite directions using electric current, now you're no longer working on an R-squared loss rule for bouncing around. You're literally going, I'm going to pull you through you. Like your electrons are going this way, your protons are going this way, and I can crush you together, and there ain't much you could do to say about this because we're using current density instead of heat. And it's a whole different
that's
animal.
Exactly what Yes, Neil, this is exactly what I think is happening. We can destroy elements with electricity, and we can build elements with electricity. And we need electric engineers like yourself to help out with that, right? I'm not an electric engineer. I know something about the elements. But you can explain how electricity can crush things together. That is dipolar in nature already, right? It's just a cluster of dipolar things. And if you can explain how they crush together, and I understand this, and every observation we make, I think there are many fusion processes going on everywhere in the universe, including on planets and whatnot, in biology and everywhere. But stars, these are those shells that they talk about. This is an illogical model. It's just a model to explain the growth, but it doesn't work. It would never work if you think about it, how it really, the steps go.
Ironically, it's kind of similar to how we envision the Earth having these layers where, in actuality, we know that there is a density change at the outer core. That we know.
Well, I'm deadly serious by suggesting that the Earth has been a star. I'm deadly serious there. I've been suspecting that for a long time now, and now I'm throwing it out there. Uh, there are many reasons for it.
Actually,
First of all, we are way too heavy. We have a strong magnetic field and all that stuff, right? There is a lot of iron here, and it totally follows the evolution model in element building, because as I see the universe, the stars have a function, the planets have a function. The stars are the breeding chambers of the carbon nuclide, carbon, which is the icosahedron. That is a fundamental thing in the whole structured atom model. I'm sure you guys have seen it a little bit.
Yeah.
That's the icosahedron, right? That sphere.
Yes.
Without that sphere, you have no other elements. You cannot put them and crush them together and all that to get all the elements. Stars are the breeding chambers for that carbon nuclide, whether it's in an oxygen or in a carbon or in a nitrogen or in a neon. That nuclide is like a seed for the rest of the fusion processes to happen. We can call those cold fusion processes.
You know what? It's actually that they're probably just because everything likes to be, as you noticed, electrically speaking, likes to be in spheres or as round as humanly possible.
Yep,
and,
exactly.
That's the same thing we notice at a certain point that planets, matter will get arranged that way, not because of gravity, because they were crushed that way. Your idea that this Earth was once a star is not as possibly crazy as we think, but it could just be a reaction to being not just part of a planet. See, one of the things that I've noticed is that things like Mars seem to be a crust of a planet that was pulled up and just shaved off, made round, and then parts went flying. But the Earth has much more dynamic processes going on, which is why, is it made of this? Is it a bunch of spheres that were crushed together? Is it a geode, type of thing? These ideas, is it hollow? Maybe, stuff like that we could be arguing and debating. The hollowness seems to be something that, because once you have an inner surface, everything that's happening on the outside must also, all the energy expressed on the outside must be expressed on the inside as well. So you can see the amount of heat because the surface area is a lot tighter. You can get fusion down there because of this idea, because you're basically taking the entire surface of the Earth, for example, and looking at the change of density between the outer core and the inner core. And imagine the inner core is a vacuum or just a hole, and it's being pushed. It would have to process all these electrons would be passing through that area as well. It would be very interesting to imagine the amount of because the energy density would be so much higher, because that sphere size versus the full sphere size of the Earth having the same amount of coulombs, yada, yada, yada. Do the math. It's very interesting what you'd be running into down there. But you could also, it hasn't escaped me, of what happens if a star or a planet went free. For example, flying through interstellar space, could a planet survive? Well, if it has a magnetic field, it would be pulling in, like the Earth, it would be pulling in a current or ions or whatever down the poles, and therefore you could see that it would have the ability to process electrons. So we could have an aurora, and our thermosphere could get quite hot. Like, let's say, like right now it's 1,500 degrees or so, our thermosphere, which is our corona, we'll call it. But this thermosphere could raise to, let's say, something 6,000 degrees. But remember, the density, it's not, the density is very thin up there, so it might have high temperature, but it's still not, incredibly deadly. But that could be radiating down upon the Earth, the surface, I mean, and keeping everything warm. We could be literally flying through the vacuum of space without a star, and we could actually survive, which is something I never considered before. Very, very.
Me neither, but now that you mention it, we might be producing our own light. Maybe not so much, but...
Well, we have an aurora, but yeah, but if we left imagine we flew out of that, we left the solar system, and we were just plucked out and put there on the edge of one of those little circuits. Well, we have a magnetic field, so we have an electric field, so we begin the process of the same thing as a neon tube. You would start pulling in ions close to the surface. It would attract all these ions to it. The ionosphere would get huge, and then if it hit a certain point, it would enter glow mode, and you could see where this is all going. So You'd be a
Well,
white
I reckon
dwarf,
we do that now,
you know?
and that's why we see the northern lights a little bit. But it's as you pointed out before, the sun is well, at least that's how I see it. The sun is drawing away the current, if you will, from Earth, right, deflecting it.
I feel it is. I feel, and no offense to Jim, because I know that his idea has to do with these rings, but I have a strong feeling that the sun is what's powering our Earth now. What the ions passing by it through the solar wind is what's giving us our current, as opposed to the actual current that's feeding the sun. Because if it's iron, it's pulling in all the magnetic fields. It's just like, I want them. You know, that's, I mean, you can really see this difference if you look at things like when you're talking with Eric Lathwaite, and he goes, here's a transformer. Notice how efficient it is if we don't have a core, if we just use air. Well, here's what happens when we put an iron core in it. You slide an iron core in, it just, boom! It's just like a powerful magnet suddenly. You know, because of the nature of iron, for some reason. It just takes magnetic fields and concentrates them. So, anyway.
What do you think, Jim?
Sorry, Jim. Go
No.
ahead.
Well, I'm still back on that point of like fusion at the solar surface, that it doesn't have to be anything to do with current. We can have it going on even with variations in current to the sun, just because there's a dynamic at the solar surface that you have to realize. It's not just that that balance of gravitational and electrostatic forces, but when you realize how strong those forces are, what it means is that if you have say a carbon ion missing X, okay, you take another electron away from it, it's not just going to drift slowly upward or downward into the sun. It has to change its radius in the sun, because that's what the balance between electrostatic forces and gravitational forces are what does that. But I think what doesn't get impressed on people is just the absolute strength of those forces at the solar surface. But what it means is if you have a transition, if you just knock an electron, one more electron off an ion, it doesn't just drift radially up or down. You've got a particle accelerator that drives it radically radially in or out to where it's supposed to be. I mean, just from that one transition. And so anything, photoionization or anything that's going to knock an electron off or get recombination, you don't just get drifting up and down out of the sun. You've just made a particle accelerator that's going to slam one nucleus now into another. So you should, what I'm getting at is ignoring totally the any current coming into or out of the sun. You should have fusion reactions at the solar surface, just because an ion is not an ion. It's not fixed for all time what it is. As you get recombination or ionization, you should have radical accelerations up or down in the suns to match that balance of electrostatic and gravitational forces. And to me, that's where you can get fusion just from a static sun, even without current flow to it. You should have fusion just from that.
Well, that presupposes, of course, what caused the ion to occur in the first place. But you're right, ignoring that just alone. And a lot of people seem to fail to understand how that the forces that are holding the surface of the sun together, if it was iron especially, are very strong. And gravity has been obviously lessened. So crushing an arch is hard. You know, like it's physically, its structure is not going to press very easily. And the idea that it's pulling towards the center point is no longer there. Basically, gravity being something that occurs on the surface of an object as opposed to crushing it into, like, what crushed into a sphere was the electrical force, made it an electrical ball. But looking at it right now, what you're just proposing, yes, it would seem that depending on voltage, if we were to put this into, I want you to look up a view there.
Yeah.
Something on a gas discharge tube or Crookes tube, or go gas discharge tube, like that, and go to images. Oh, you're already on images. Okay. There's some one with go up a bit. Oh, that's a good one. Perfect. So this is what we're looking at here. You have the cathode and the anode. The anode being the surface of the sun. This cathode being something that's like, say, the beginning of the double layer above it, where all the giant tornadoes of fire, the anode tufts reach to. You would see how there's different pressures inside this tube. Yeah, go either one, it doesn't matter. But you see that there will be different potentials in this area. Like some places have, if you look at other images, would actually show you what you're looking at in here. But they're like that one, that blue one, right there. See how there's layers in this? Each one has a different ionization potential because it's not even. The voltage steps are not even. You get different densities as you go on. To get rid of those, that's what happens when it goes to arc mode in a gas, for example. But the arc mode in a gas, the reason we use noble gases is because they don't react. That's because we want to make light with it, right? And we want the light to be stable. But if you start using gases that react, shit happens. And they no longer have the same color or anything like that. And you can see how these steps can occur in different gases and so forth. So this potential is what we're talking about, and you can, that's a perfect look of it right there. And so this is why, and that's stacking. Those bunch of stacks there, those are going out from the sun. That's the little corona down near the base, and then down near, even closer to the surface, you have this area that's sort of off. You can't see it clearly from here, but you see how it's not as dense down near the right side base. That's the air gap just above the sun. And this is what you're looking at here. So the planets exist in that pink area out there near close to the cathode.
Which way do the electrons actually flow, Neil?
Well, they flow electrons go from cathode to anode, and so the electrons flow to the anode, and then cathode has ions flowing off of it, and they're colliding there in the middle, which is what makes them glow.
So in this case, they go from left to right.
Yes, that's cathodes or minus charges are going to the right, and ions are going to the left.
Yeah, but cathode is negative, and the negative flows towards the positive in this case.
That would be the heliopause way out there. The right,
because there's always confusion. There's always confusion in which way the electrons flow, and there's also confusion between electric and chemical batteries and stuff. Depending how you look at it. Right, I'm always confused.
Let me explain that. If you can go back to that picture, I can explain why that is like that. Even when you look at the colors of them, you can see the wires leading into it. I don't know where it was.
Find it again.
Yeah,
we
totally ruined it, man. You totally
ruined the blue one will work.
Oh, man, I was close. Yeah.
So close. Anyway.
It's
up on the right. It's up a couple rows on the right.
Oh, thanks. Okay.
Go in. There you go.
There it is.
Okay. All right. Yay!
So notice the red. That would normally we would call positive, but that's because it's conventional. And like I said, conventional is reversed. But this convention only works with actual wiring. It's not as important when we start talking about the word anode and cathode, because when you start using those words, like the sun is an anode, and the Earth is generally an anode as well. But at a lower potential, obviously. This is the positive. That's the positive side. So when you see anything that says anode and cathode, you could always know that cathode is the one sending off the electrons, and anode is sending off the ions. Interestingly, though, the ions that are coming off this can't actually combine with anything. They can only run into things because of the fact that it's a noble gas in there.
Right.
If it was a reactive gas, and imagine we just start, we have a little throttle here, a little knob that we can turn the voltage up, and therefore we're changing the current density, and so on. Now imagine that this is a radial tube. So basically there's a wire leading up to a ball in the middle, and this is a bigger ball, which is a cathode all the way around it. Now we would start losing those little bubbles because current density would be significant. It'd be radially decreasing. But you can see what I'm talking about here. You just start cranking to a certain point, and that corona, the anode glow down near the base, would have some crazy crap going on in it, I'm sure. And this is why we see nuclear fusion, more or less.
Where in your book, Neil, and Jim as well, please, and anybody else, what would be the likely place, if you can pinpoint it, for fusion processes?
I would say right where that black wire is reaching into the thing. Although in the tube, that part
that
where
would
it's
be
at,
the metallic surface, if you will.
well, just above it.
Just above it.
Like that.
I do believe Safire points out there's a huge potential jump there.
That's we also have the most thermal energy as well.
And that's what Jim was alluding to as well, I believe, that force is so strong there, that opposing force, the way it's ripped apart, right, Jim?
Well, see, that's where Safire. I'm not diminishing what they're doing. I mean, if they get, those are important experiments, but they're not doing.
Those Safire guys are just terrible. I don't like them.
Well, yeah.
Just kidding. They're great.
What they're absolutely
they're doing good stuff.
Yeah, but they're absolutely not duplicating what's happening at the solar surface just because of that.
Because of what?
Obviously, well, gravitational forces obviously aren't going to be significant in the lab, and solar formation. They're not doing an experiment in solar formation. They're starting with a sphere and then creating what looks like a solar surface on it, but even the mainstream knows that it's the filaments that came first, and that somehow you get star formation. They'll have it by gravitational collapse, but what Safire absolutely isn't doing is getting the surface of their little sun based on any balance of any. They're starting with that. Now, there are experiments for electrical fusion. That's important, but they're not even close to duplicating what's going on at the solar surface, just because they're missing that, radically important.
I agree. Some factors are missing to make the model.
And that's an important one. So even with that mainstream, but that came from a calc.
I need to point out that, in my opinion, that wasn't their goal. What they basically built was one of these that we're looking at here, but just as I described it, with a point, the anode being the ball in the middle, and then the cathode being a big ball around it, a metal ball. Mm-hmm. And then they put a bunch of probes in it, just like the probes that are around the sun that we currently have, that detect voltage potentials and so forth, the ones that the SOHO satellites and stuff like that. And basically what they're trying to do is imitate those readings that you get from space and show that we can get them here in this model. That would be a long way of proving the concept of an electric sun, which I think is their goal, not, in my opinion. I don't think that they're really working on the surface as much as, like, me and you have probably done more in that regard, just talking about it, than they probably do, because it's not their end game, I don't think.
Right. See, the whole point of gravity, though, the important thing, that the force of it is so strong at the solar surface that it will accelerate if you have an ion floating at a certain depth, and then you change its state. It will radically accelerate. So, in other words, you don't need even to have external current to get fusion at the solar surface, just because of that crazy balance of forces. And that's really, though, where I really wish that you would have picked that up. Like when that article on the global electrostatic charge of stars. When that came out, it was a reminder to the mainstream, to who obviously knew about the gravitational forces, is to remind them that, hey, right here, electrostatic forces become significant. But
what about on Earth?
What's that?
What about on Earth, Jim? If we go down in the Earth, from the surface level, and we go down 20 miles or something to that effect, 30, 40 kilometers, we hit a transition zone that is very abrupt, and it's pretty hard, I believe. It's like below it is a mantle, and they're very separated. Allegedly, according to Mr. Krivitsky from Russia, he's a geologist, a chemist geologist. He points out that the pressure down there is, first of all, very, very huge. I don't know how many atmosphere, but you're talking a huge amount. I think millions of atmospheres. And you're talking, if there's a heat and an electric going on there as well, and those forces that you talk about, would that be enough to ignite certain fusion processes, if you don't think too conventionally that is?
Yeah, now you're asking the difference between you're replacing pressure with gravity as far as.
Well, yeah, more or less.
I can tell you what I think really very simply is that where you have at 50 kilometers away from the Earth, you have an ionosphere. Varies between this and that, but that's where the quote-unquote giant tornadoes would be connecting if this was the sun. So let's just put the ionospheres here. Now, you have to have something that is keeping that charge from slamming into the Earth. It's very attracted to that negative surface. It wants to get there. It goes to the tops of the mountains. It goes to the tops of high points. Anything it can to get to that surface, which is what causes lightning and everything else. Well, here's where things get kind of weird, which, God, that's a very beautiful picture. But there should be, or there has to be, like I said, a positive ionosphere under the Earth, inside of it, repelling the one that's in the ionosphere. That's just what's going to happen. So the same thing would be happening with the sun. If there's a voltage potential at the sun's surface, there is an inner voltage potential equal to that. Because remember, it has to keep that. It's basically the likes principle. So it has to. The positive ionosphere is attracted to the negative surface, but it can't touch it because there's a positive on the other side that is keeping this balanced.
In simple terms, what makes the sun an anode or the Earth?
More or less, yes. So the higher the current density and the more vibrations going through it, the more this effect occurs, and the more it attracts more ions. And of course, at a certain point, it's going to hit a balance, and that's what we see. I think that is where the mantle starts, and that is why we see currents in it, or they say a flow of iron. They said, but basically it's the inner jet stream. There's a jet stream around the pole of the planet. Well, there's an inner jet stream around in the surface of the Earth that's induced by that one. And see it just like that, just like it's spinning, just like you see it doing that. That's exactly what it's doing. And it's doing it for the exact same friggin' reason. So, these ring currents are at the north and south, and that's why we have a sort of a
would they connect
at the neutral point in the middle too, but you don't see it in this picture because they're not as concentrated.
Now, if you throw in the electric circuitry of Bruce, then you get short circuits between the upper and the lower part, if you will. That would be your mid-oceanic ridge.
Well, whenever they make connections, they're gonna try to short out, just like basically underground lightning bolts or.
Well, it's still one metallic object, so charge would distribute, right?
Right, and it's not even. This is what I was going to say. When you were talking about this, Jim, I wanted to point out that when we were talking about the surface, we have this vision of the surface looking like this, perfectly smooth and everything else. But if the iron or surface model is correct, we'll just go with that, Then you have mountain ranges, which are pulled from material that has been deposited from other prominences, and then they become differently charged to different parts of the sun, which cause these loops to loop around. And of course, they're induced by the current going around. So you're going to have concentrations where elements are formed, and then they're going to stop being formed there and be formed somewhere else, and so on and so on. And this would change depending on density. There should be cyclic rations, which is what we see with sunspot cycles and so forth. That's just an interpretation, but correct me if I'm wrong.
Well, I'm not going to correct you because that's where I'm basically going, Neil. What you just told us. I think this is the prime mechanism for everything on Earth. The whole geology is created by the mechanism that we're touching upon right now. That would be the interaction mechanism with the bigger cosmos, right? Through the sun and the stars and the planets and the bigger thing.
Well,
but it's all electric in nature, of course. And this Earth is rotating in that hole again also, the day-night cycle.
Right.
We get a whole dynamics.
Remember when I said turning it up and turning it down? Look what they're doing here. He's turning it up and then turning it down. It changes everything. If you just change one knob. It's very, sorry, I'm just blown away. Please go on.
So variation.
Right there. Sorry.
What? Any variation in the sun's heliosphere would have its impact, right? And that's exactly what we're witnessing. Any subtle change will cause a change in the weather pattern, right?
This brings us right into space weather and suspicious observers.
Yes,
they're very. I mean, this is my interpretation of the model.
Except that they're still talking sometimes about neutrinos, antimatter, and whatnot.
We gotta talk to this guy. That's an astrophysicist made this.
Yeah.
Like he's making a Terrella based on Christian Birkeland. Well, I can read what he's saying there. Actually, it might not be French. I don't know what language that was, actually.
I think it was French.
Okay. Sorry, that's beautiful. That's beautiful.
Yeah.
Well, anyone else want to add to this wonderful thing? Because I think we just basically solved everything that we need to know. We can go home now and get our Nobel Prize, because I think we win.